Alternating series test. Now, you're getting these down, I wrote a couple different alternating series. I mean, this is generally what it looks like, whatever we're working with. But sometimes you could have an n plus 1 power, an n plus 2 power, n minus 1. So this could kind of change things here. But either way, it's going to be alternating. So it just means that it goes positive, negative, or in this case, it would go, that would go negative, positive, and that one would start positive. Okay. Still going to alternate. Just give you a couple different looks here. The key would be this piece right here. So in a generic form, I said the limit of a sub n is 0. It's whatever the function is. I know this says n plus 1, but it's whatever the function is it's talking about. Okay? So the non-alternating piece, that's what we're going to look at. We want to make sure that that's 0. And then we want to make sure that this a sub n plus 1 is less than a sub n. Just remember a plus 1, that's the next term. So obviously if we had like an n plus 1 here, this would be n plus 2. Just whatever that next term is. Just trying to get, you can't write when you write the rules up there, they're pretty generic. We can see some different forms, okay? So just remember that this is referring to the limit of the function. I'll just call it the function equals 0. So the non-alternating part, and then the next term's less than the original. That's the idea. Right. Now, the alternating series test. The nice thing is it's pretty simple to tell if you're going to use an alternating series test. An alternating series test only works on an alternating series. If it's not alternating, you can't use it. Okay. So then it'll be back to anything else that we've talked about. Okay. So an alternating series looks something like this. Let's go the sum. N goes from 1 to infinity. Negative 1 to the n. 1 over root n. So the first thing I want to check is if in fact it's alternating, and when I see that negative 1 to the n, yes it is. And 9 times out of 10 we do see negative 1s, but I just want you to realize if that was a negative 3 to the n, it's still alternating. It wouldn't really matter if it's a 1 or not. It's that negative value alternating back and forth. Okay, so we know it's alternating. That's going to let us apply this. We need to check the limit of the function. So the function, again, is the non-alternating part. We're looking at that guy. Okay. I'm going to look at, let's see, the limit is n goes to infinity, 1 over root n. And the question is, does that equal 0? Did I give us 0? Okay, so part 1 done. All right. So I need to verify that that equals 0. It does. I need to check my next term. Here's my next term, 1 over square root n plus 1. Whatever the next one was, I have the nth term, so the next term is the n plus 1 term. Is that in fact less than 1 over the square root of n or not? Yeah. That's less than because that denominator is bigger, right? So that's true. Both parts satisfied, converges. Either part fails, diverges. But we got to show that both parts are satisfied. Now the nice thing is for us, other than the fact of recognizing it's alternating, which I think that's pretty easy most of the time, okay? The rest of the stuff we've kind of done. If we know how to do a limit, okay, we can tell if a limit equals 0 or not, and we know how to check to see if one term's less than the other. We saw that recently. So not a lot new here as far as what we're looking at. We're just seeing a different type of sequence. Let's go n plus 1 to infinity, or n equals 1 to infinity. Plus negative 1 to the n plus 1 times n plus 1 over n. Checking if it's alternating. I don't care if that's a M plus or minus, whatever, that's still going to make it alternating. Okay? This one would just start with the positive instead of the negative like the previous one. So it's alternating. Okay? I'm going to check my function piece here. So I'm looking at this guy right here. The part that's not the alternating piece. We're going to look at the limit. N goes to infinity of m plus 1 over n. Does that equal 0? No, what does that equal? 1. All right. I'm just going to put a big X there. No. Limit is 1. That'll help you in your notes. It's not 0. Diverge. I don't care if the n plus 1 term is less than the nth term. It didn't satisfy both cases. Okay, so no need to go to that one. But if I did go to it, yeah, that denominator is going to get bigger. Change anything there, but it's not going to matter. So I need to satisfy both pieces. Are you okay there? All right. Not a whole lot on an alternating series test. All right. We got to make sure it's alternating. That's number 1. 2, make sure the limit equals 0. It either does or doesn't. Okay. And then 3, make sure the n plus 1 term or whatever the next term is less than the original. It either is or it isn't. They're convergent. Right? Alternating also brings in what we call absolute and conditional convergence. The sum of a sub n is absolutely convergent if the sum of the absolute value of a sub n converges. The sum of a sub n is conditionally convergent if the sum of a sub n converges and the sum of the absolute value of a sub n diverges. So basically, this idea, as you're writing that down, is kind of trying to decide, do we need the alternating piece to make it converge? Does it only converge when it's alternating? Will it converge when it's not alternating? And so it's really investigating kind of like these pieces I have in green here. So we'll look at a few of them, but if I were to take the absolute value of each one of these, I would only be looking at the part that's circled in green. The other part would be irrelevant. So if it was the absolute value, it wouldn't alternate. Everybody okay with that? So looking at that piece. If you're trying to determine or you're asked to determine if something has absolute or conditional convergence or divergence would be the third choice through, I would always check the absolute value first. Because if it's absolutely convergent, you're done. If you determine that the absolute value diverges, well, then go check the alternating series. So if the absolute value diverges, but when it's alternating, it converges, that's conditional. In other words, it's saying it's on the condition that it has to be alternating. That's the only way it's going to work. Are you okay with that? If you check the alternating series test first to determine this, you're still going to have to go back and do the absolute to determine if it's absolute or not. So that's why I would suggest doing the absolute part first if you're asked to, because then if it works, you're done. If it's not, you go to the next step. That's the nice part. It can save you, I guess you could say it could save you a step on half of them, not all of them. So let's look at some here. We're going to take a look and see, are we absolute, conditional, or diverge. So when I'm saying absolute or conditional, I'm referring to it converges. Absolutely or conditionally. Let's go with this guy. N goes from 1 to infinity. -1 to the n plus 1, 1 over cube root n. Now, if we're determining if something has absolute or conditional convergence, we're still talking about an alternating series. So we do want to make sure it's alternating. It is. The -1 to the n plus 1 is going to produce an alternating series. Not a big deal there. Right? So what we'll do first is we'll check the absolute. I'll just put absolute question mark. So if I take the absolute value of this, that means I'm looking at the sum as n goes from 1 to infinity of just 1 over cube root n. Now you can put the absolute value symbols in there or not, but the idea would be, I'm kind of skipping a step. If I put absolute values around this, it's basically just going to knock out the -1 to the n plus 1. So it's just going to leave the other. It's just making sure that it's always positive. Everybody okay with that? All right. So now this is what I'm investigating. So this goes back to any of those other tests we've done. What do you think? 1 over the cube root of n. Converge, diverge, reason.
Converge to 0.
Or both, converge and diverge.
Isn't that like it diverges? It diverges.
It's less than 1.
Yeah. P. This would be a P series. 1/3, right? Okay, now is less than 1 converge or diverge? Okay. So less than or equal to 1 is diverge. So absolute? No. Not absolute. That means now I'm going to see if the alternating part does. If the alternating part converges, then we say it's conditional convergence, because it's conditional on being alternating. If it doesn't, then it diverges. So now we're back to alternating series test. I'll just put alternating series, question mark. Now we already know it's alternating, so we have 2 things left. Does the limit equal 0, and is the next term smaller than the original? So I check my 2 pieces. The limit, as n approaches infinity, 1 over cube root of n. So the question is, does that actually equal 0?
Yes.
Yes. All right, we're good there. All right. n plus 1 term, does 1 over the cube root, n plus 1, is that in fact less than 1 over the cube root of n? Yes, both parts satisfied. So we're back doing the same test we did before. Okay? This is going back to old stuff. This is what we were just talking about before. So, hey, yeah, this works. So we say this is conditional. I'll just say conditionally convergent. So we're going to check the absolute. If it is, we're done. If it's not, we go to the alternating series test, see if it works on that. If it does, it's conditional. If it doesn't, it diverges all the time. We're okay there? Okay, let's go to the next one here. All right, there we go. N goes from 1 to infinity, -1 to the n plus 1 over n. So we're going to check the absolute first. Sum as n goes from 1 to infinity, 1 over n. Converge, diverge, why? Diverge, harmonic. Diverge, P series. However you want to, we got a few ways we can do that one, right? All right, so no. All right, alternating series. Check my alternating series, see if it converges or not. So we got two things to prove. Limit as n goes to infinity of 1 over n. Does that equal 0? Yes. Is 1 over n plus 1 less than 1 over n?
Yeah.
So we have conditionally convergent. Now here's a nice piece that can help you remember. Harmonic diverges. Alternating harmonic converges.
I'm not sure I understand what you mean by conditionally convergent, because we know that it is alternating. So if it's always alternating, why would you say it's, I don't know how to say it.
No, so the conditional part means that it only converges when it's alternating.
Okay,
An absolute convergence would mean that it converges whether it's alternating or not. So if I took the alternating piece away, it would still converge.
Okay.
It doesn't matter if it's alternating or not alternating, it'll always converge.
okay.
Conditional means it has to be under the condition that it's actually alternating. So here's a good example, since we've talked about this one before. The harmonic one, through whatever test you want to use, is a divergent series. But if you alternate that harmonic one, now it converges. So an alternating harmonic is a convergent series. A harmonic's a divergent. So under that condition of it being alternating, that's what's going to make it converge. And the reason is pretty simple if you just think about it. I mean, you'd have to write them out to see them all, but if you're going plus minus, plus minus, plus minus, things are going to start canceling out down the line. That's what's happening there. So it would be that same one. All right. Let's go with this. 1 to infinity. -1 to, let's see what I have there. To the n plus 1 over 3 to the n. So check the absolute first. So when I check the absolute, it's basically going to take out the numerator. In other words, the numerator would always be 1 here. It's just not going to alternate. Okay? So my investigation is 1 to infinity, 1 over 3 to the n. Okay? So now I'm going back to the stuff I've learned. Does that converge or diverge? Reason.
That converges because they're geometric and it's less than 1.
Geometric. That looks like it's geometric, but
What just came out?
remember how he said sometimes it's kind of a pain with just on the bottom, but you can actually rewrite this one to that, right? Because of the 1 up top. All right, so this would be the geometric, not the p-series test, because now n's the power, not the numerical piece of the power. All right, so r equals 1/3, less than 1. Converge or diverge? Converge. That's where I used to get mixed up all the time, because I get my p-series and geometric backwards. Okay, I know they're opposites, but if I think of it backwards, I've got them both wrong. Okay. So that converges. This is a yes. We're done.
Yes.
This is absolutely convergent, which means that it's going to converge all the time. I don't need to go check the alternating piece. It's still going to converge. Okay? It's absolutely convergent. That means it's going to happen all the time. Conditional means it had to be an alternating piece to make it converge. Okay? And again, if both parts fail, we're looking at a divergent sequence or series. It's not going to change anything on that. So some little variations here today, because we've got the alternating piece that shows up. Okay. If we're asked just does the alternating series converge, we're just doing the alternating series test to see if that alternating piece does. If we're asked if it has absolute or conditional convergence, then we're checking that absolute one first to see if that works or not. Okay? Other than that, it's going back to some stuff that we're pretty familiar with. You know, we're not going to be the best at all these old tests. We're still getting them down, doing a pretty good job, but that's still stuff we've done. Okay? We're pretty good at limits. We know if a limit's going to be 0 or not. Okay, we still make mistakes from now and then, but we're pretty good. We're pretty familiar with that. This was a little new the other day, that n+1 term, but now we've gotten down, well, if the denominator's bigger, it's going to make the fraction smaller. Makes sense. Something like that. All right.